SwayamPrabha. Digital India. Educated India.
Hello all. In this video we'll be looking at the strength properties of a lamina. Until now we have been looking at the stiffness of the lamina, where we have looked at the stress and strain relations. But strength is also equally important, especially when we want to design these composites using the lamina. Meaning we want to know when does this lamina fail when we design. So these loadings may be as simple as uniaxial loads as well as complex as biaxial or triaxial loads, meaning loads acting in two directions or the three direction loads. So in this combination of loads, how do we assess whether a particular lamina fails or if it is safe? For that, we will see what are the uh, properties we have to look at for the strength of a lamina. So we'll start with defining few fundamental strengths in a lamina. So we'll start with X. X refers to the axial or the longitudinal strength in the direction one. So let's say we are looking at, so let's say the fibers are also in this X direction and the loading is also in the same direction. So essentially we are looking at what stresses this lamina will fail. That is represented by capital X. And for the same lamina, if we start applying a transverse load, meaning still the fibers are, let's say, along x-axis, but now the loading is perpendicular. So now if you are looking at the stress at which it fails, that gives you the transverse strength of the material or the strength in the second direction. Mind you, we are currently looking at strength in the material coordinate system, which means we are looking at either along the fibers or perpendicular to the fibers. And lastly, we also look at the shear strength, meaning for the same lamina, if we apply a few shear, at what stress it fails. That is recorded using this variable S, which stands for the shear strength. So mind you, what we are now looking at is, we only talk about axial strength or the transverse strength. We never mention whether the loading is in tension or compression, because if we are considering an isotropic material, it has most often the same strength both in tension and compression. But when it comes to composites, it is evident that these strengths in tension and compressions are very different. So they need to be written using a different format, which we will show now. So before we go there, we first see the way to define the stiffness of a lamina. We used some engineering constants. Essentially, for a 2D state of stress, we used four engineering constants, which are E1, E2, Poisson ratio nu12, and the shear modulus G1. Similarly, for the strengths, we will have a series of material constants which are shown here. So here xt refers to axial strength in tension. And xc refers to the same axial strength in compression. Same things for yt and yc. The only difference is these are transverse strength in tension and transverse strength in compression. But when we look for the shear strength, we see that either we apply the positive or the negative shear, it doesn't matter. Both give you the same equivalent stresses along the fibers. So both the loadings will end up with the same strength S. This is only true if you are applying a pure shear in the material coordinates as shown here. But of course, later you will see, or if you refer to any standard book, you will see this is not the same if you are loading in an off-axis direction, meaning at an orientation. There, whether you are applying a positive shear or a negative shear matters, but if you are applying it in the material coordinates, it doesn't matter. Currently, we showed the strengths in terms of stresses, but the strengths can also be shown in terms of the strains. So for axial strain in tension, we write it as x epsilon t, and axial strain in compression, we write it as x epsilon c. Similarly, for transverse strain in tension, we write it as y epsilon t, and transverse strain in compression, we write it as y epsilon c. And corresponding to the shear strength, the corresponding strain, we write it as S epsilon. So we can write these failure strains in terms of the failure strengths by simply writing it as xt by E1, this as xc by E1. For the transverse strains, we'll write it in terms of yt by E2 and yc by E2. And lastly, for the shear strain, failure shear strain, we'll write it in terms of S by G1. In summary, what we have learned in this slide is, for stiffness, we use 4 elastic constants E1, E2, nu12 and G12. But for strengths, we will define it with 5 strengths, which are XT and XC, standing for the axial strengths in tension and compression, YT, YC for transverse strength in tension and compression, and lastly S for shear strength. And for all these 5 strengths, we have the corresponding failure strengths given as this x epsilon t and so on and so forth. And we have also showed that this failure strain can be written as the ratio of the failure strength by the corresponding modulus. This is all possible because we assume that most materials behave in a brittle fashion, meaning they respond in a linear elastic fashion until failure. Now let's quickly look at what are the few tests one can do to find these strengths. So let's start with, let's say the fibers are horizontal here, and then we apply a load along the direction of the fibers. So let's say this is the only load, and then from this single experiment we should be able to find few material properties, such as we should be able to find elastic constant E1, where we can define as stress by strain. So let's say we applied a stress sigma 1 and we have received epsilon 1. This should give us the modulus E1. And we can also find the Poisson ratio nu12, where we can write it as epsilon 2 by epsilon 1, meaning we need to find the strain in the transverse direction as well as the strain in the axial direction. If we measure both of these strains, one should be able to write this Poisson ratio nu1. But in addition to this, we can also find, in this case, xt, because if you are looking for the stress until failure, that should give you this xt value. So let's say the response of this material is something like this. It shows linear response until failure. Let's say these are the stress and the strain. The corresponding stress at which it fails, we will now call it as xt, because here we have seen we are applying a tension load. And the corresponding strain, as we have shown in the previous slide, this is x epsilon t. This is the corresponding strain to failure. Similarly, we can do another experiment with the same material where the fibers are in the x direction. Now we can apply the load in the perpendicular direction. Let's say this is sigma 2. From this experiment, what are the things we can find? We should be able to find what is E2. E2 is simply sigma 2 by strain in the direction which is epsilon 2. And then we can also find Poisson ratio nu 21, which is given as epsilon 1 by epsilon 2 when we are loading it in the second direction. Here you will see that nu21 is redundant because we already know what are E1 values, E2 values and Poisson ratio nu12. But if we are doing an experiment, it is good to find this value, because if you see this and you can relate with the relations between both the Poisson ratio, if it matches, it only confirms that the analysis what we are doing is correct. But if there is a mismatch, then one should doubt the experiment, meaning the data collection might be wrong, or maybe it's also possible that the material is not linear elastic, because this relation between the Poisson ratio is coming from linear elastic assumptions. So now if we say that assumption is not valid, then of course from this experiment we can say that it is no more a linear elastic material, and probably we have to use a nonlinear elastic analysis. But in addition to that, we should be able to find this YT value, meaning the transfer strength in tension. Later, if we can replace this tension loading with compression loading, we should also be finding what is the YC value. So what we are trying to show is these simple experiments will give you some of the elastic constants and the strengths, as well as the strains corresponding to those strengths. But neither of these two experiments will give you any shear properties. So for that we need to apply a shear load, but in practice applying shear load is not as simple as applying the normal loads. So usually people come up with different strategies to apply shear. There are several things you can find in the literature, but here what we'll show is, so we'll have this specimen, but this time we'll have the fibers, let's say at 45 degrees, and then apply uniaxial stress. Now we'll call it as sigma x, because now we are looking at a body coordinate system. So earlier we have shown these stress strain relations. From that relations we can show that 1 by Ex is written as 1 by 4 times 1 by E1 minus 2 nu12 by E1 plus 1 by G12 plus 1 by E2. So from the experiment I should be able to find out what is Ex, because Ex is simply sigma x by epsilon x. So meaning the applied stresses by the measured strain in that direction, or the normal strain along the loading direction. So this we are getting from the test Ex. E1 we have seen from the previous slide, the normal simple test where we applied an axial load along the material coordinates. We were already able to find out these values of E1 and E2 as well as the Poisson ratio. So the only unknown quantity in this equation is G1. So first from the experiment we find Ex, and using this relation then we can estimate what is the corresponding shear stress at that failure. So though people use this test, it's not the best of the test, because even in this condition there are some problems, meaning that how we hold the specimen is important, because if we look here, it's a generally orthotropic material, meaning there is extension shear coupling. When there is extension shear coupling and we apply, let's say, a uniaxial stress, then it's bound to have some shear. But at the grippers, do we allow this shear to occur or not will play a role on the measured loads. So as we see, if we look closely, there are some problems even with this test. So people have come up with better test, but bear in mind that testing a composite under shear is a challenge. There are tests which are now better, but each test has its own limitations. So let's summarize what we have discussed in this video. So we introduced some fundamental strengths for composites, namely XT and XC. These are the axial strengths in tension and compression. Similarly, the transfer strengths in tension and compression are YT and YC. And S is the shear strength. Here we are only looking at one component because we said if you are applying a pure shear for a composite or a lamina, then whether you apply the positive or the negative shear, both will end up with the same value because the positive or the sign doesn't matter. But this is only for pure shear what we are applying. And corresponding to each of these strengths, we said there is a corresponding strain of failure, which we represented as x epsilon t, x epsilon c, y epsilon t, y epsilon c, and s epsilon. Since we are only looking at the linear elastic, we also have showed how we can write this failure strain in terms of the failure strength and the stiffness in that direction. So we will use these fundamental strengths in the coming videos to show how we can predict failure not just under uniaxial loads but also in biaxial loads where we have loading in two directions, but still we are able to use these fundamental strengths to predict. So there we will see that we will be looking at couple of failure criteria and see how we can apply those failure criteria to predict whether there is a failure in this lamina or not. So with this, we will conclude this video and see you later.